Today's tactical electronic aircraft systems are becoming more and more vulnerable to enemy-directed energy threats from the air, the sea, and the ground. These foreseeable threats can be in the form of high-powered microwave, electromagnetic radiation, and nuclear radiation, and will be able to knock out or effectively jam electronic flight control systems of tactical naval aircraft, rendering them ineffective. Add to that the fact that future high-performance Navy aircraft will become increasingly unstable, and it becomes clear that a non-electric backup flight control system is needed. Such a system would have to be immune to all forms of radiation. It would also need to endure environmental shock, vibration, and temperature extremes, and it would have to be integrated with electronic flight control systems. Such a system would use Fluidics. Developed at the Naval Air Development Center in Warminster, Pennsylvania, Fluidics is the only non-electric control technology capable of stabilizing modern high-performance fighter attack aircraft. It's also totally immune to all kinds of electromagnetic interference, including foreseeable directed energy threats. The Naval Air Development Center developed and evaluated in flight test a fluidic flight control system on board a Navy T-2C twin jet carrier aircraft to see if it would be a viable backup to the digital fly-by-wire system, which is currently the Navy's primary flight control system.
Today's modern tactical aircraft are built dynamically and statically unstable. This instability allows greater maneuverability. The problem with the instability, though, is that it's very difficult for a human pilot to fly the airplane unless we incorporate an electronic or fly-by-wire flight control system. Electronic or fly-by-wire flight control systems, though, are very susceptible.
What we have on the T2 is a lateral directional flight control system, full authority, using both fly-by-wire and fluidic flight control systems. The fluidic system uses engine bleed air. There's an aileron control package and a rudder control package in the empennage. There's pilot inputs and trim signals, and the rudder, in addition to these, has a yaw stability augmentation input summed into it. This is the actuator from the flight test of the T2. It's a dual mode actuator. This is the fly-by-wire section. This is the fluidic input. Fly-by-wire is a direct drive actuator using a samarium cobalt motor with electrical command coming in here. The currents produced by that are moved in the field, causing the servo valve to move and porting oil of 8,000 psi power into the extend and retract sections of the actuator. To see how one of these stages of amplifiers works, well, under this cover we have a fluidic stack, bonded metal, something like this, about this size. It's made up of laminates stacked together in this fashion, and these are mounted on a laboratory test block so that they can be checked and performance checked and operationally checked out before being bonded together and bolted onto the actuator control interface. To show how one of these amplifier stages works, I have a slide here which illustrates a single stage of amplification. You have the power jet coming up through the stack, feeding the nozzle of the laminar proportional amplifier. The output of the previous stack becomes the control inputs for this one, and they're coming up here through the stack and coming to the control input ports. There.
During the flight demonstration phase with this program, we've been able to demonstrate the type of flight regimes that would be normally encountered around a carrier during fleet operations, and have been very successful in all those regimes. Flying as a single airplane, we've been able to go out and aggressively maneuver with the aircraft, high G onset, a lot of rapid reversals, acrobatics, that sort of flying in the fluidic flight control system, and the system has responded very well. These are the kind of maneuvers you could expect to have to use in an evasive situation or trying to get a crippled aircraft out of a hostile area. We've also done formation work with the airplane, which has again been very successful. The type of precision formation we've been doing with the fluidic system has been the type of work that you would have to do in an in-flight refueling situation where you're required to fly a precise position for a reasonably lengthy amount of time behind a tanker aircraft. And in all cases, during the parade and close formation and even maneuvering formation situations we've encountered, the aircraft has performed exceedingly well. Finally, we've been working on field carrier landings with the aircraft here at the field using the same sort of lens system we'd encounter at the ship. And all of the FCLPs that we've done with the airplane has responded extremely well again, and the handling characteristics have been more than adequate to land this airplane on board a carrier during normal operations. In all of the flight regimes we've tested, the response from the fluidic flight control system has been very crisp, very positive in all regimes, slow speed and high speed flight. In most cases, we have either met or exceeded the handling characteristics of a standard T2 aircraft. The stick forces have always been somewhat lighter than the normal airplane, and the control responsiveness has been slightly faster in the higher speed regimes than a normal T2. So we found that the control has been at least as good and usually better than a standard airplane in both the formation flying and even the landing phases. So in the carrier phases that we've tested, the airplane has been extremely successful.
What you have with the fluidic system is the best of all worlds, okay? It's impervious to electronic warfare. It provides the fidelity necessary to actually control the airplane throughout all of its tactical envelope and also bring the airplane back and land aboard a carrier. What we envision for the fluidic flight control system is not as a primary system, but as a backup system, so that when the primary and secondary system fails, should they do so, they will revert to the fluidic flight control system.
Commander Roger Hill, the program's first test pilot, probably said it best. Now let's move on and put it in a tactical airplane, like the F-18. Given the success of the Fluidics program, NADC proposed an Advanced Technology Demonstration Program, or ATD, to incorporate this system on board an F-18 test aircraft. The successful completion of this effort should prove that Fluidics is ready for introduction into the fleet. The 6.3 ATD was given first priority by Op 05, approved by Op 91, and began in October of 1990.